Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand intellectual edifice of late Victorian science, Karl Pearson's 1894 monograph, Contributions to the Mathematical Theory of Evolution, stands as a foundational pillar for the field of mathematical statistics and a profound statement on the future of biological inquiry. Published in the Philosophical Transactions of the Royal Society, this work represents a deliberate and ambitious attempt to move the study of evolution from the realm of qualitative description and speculative morphology into the rigorous, quantitative domain of mathematical law. It is a document born of the conviction that the subtle variations upon which natural selection operates are amenable to precise numerical analysis. This essay undertakes a deep, internal evaluation of Pearson's 1894 work, proceeding systematically through its core arguments. The focus remains locked upon the specific claims, the proposed mechanisms, and the presented evidence within the paper itself, assessing the logical architecture and the enduring intellectual force of this seminal contribution to quantitative biology. It is an exploration of a moment when the abstract power of statistics was first brought to bear with full force upon the messy, beautiful complexities of the living. Section 1, The Problem of Asymmetry and the Insufficiency of Normalcy. Pearson begins his treatise by framing the central problem that his new mathematical machinery is designed to solve. The prevailing statistical tool of the era, the normal or Gaussian distribution, described by the familiar bell-shaped curve, presupposed symmetry. Yet, Pearson observed from various data sets, ranging from anthropometric measurements to botanical characteristics and even economic phenomena like barometer readings, that nature frequently produced asymmetrical, or skew, frequency distributions. His fundamental claim in this introductory section is that such asymmetry is informationally rich and represents a primary target for evolutionary analysis. He posits that a symmetrical, homogeneous population, under the influence of random causes, would indeed conform to the law of errors and produce a normal curve. The presence of skewness, therefore, signals a departure from this idealized state. Pearson's central hypothesis, presented as the logical premise for all that follows, is that a primary cause of this observed asymmetry is the action of natural selection upon a population that is itself heterogeneous. He conceives of a given species or group as a composite entity, a mixture of two or more distinct subgroups, each with its own typical character. When selection acts differentially upon this compound group, the resulting frequency curve of any measured character will be distorted and skewed. In evaluating this initial claim, its power lies in its conceptual elegance. It transforms a statistical nuisance, asymmetry, into a biological signal. The argument presented is one of logical inference if homogeneity plus random causes yields symmetry, then observed asymmetry implies the presence of some systematic force or an underlying heterogeneity. The evidence offered at this stage is more illustrative than demonstrative, with Pearson referencing his own and others' observations of skew curves in crabs, prawns, and human populations. The claim rests on the plausibility of his causal model, which at this point is compelling, yet unproven, biological scenario. The internal logic is sound, provided one accepts the premise that evolution operating on mixed populations is a common and potent source of observable skewness. His work therefore sets out to build a mathematical framework capable of dissecting this skewness and revealing the underlying structure it supposedly represents. Section 2, The Mathematical Decomposition of Asymmetrical Curves. The theoretical heart of Pearson's paper is his mathematical solution to the problem of asymmetry. Having established the conceptual need for a more general theory of frequency curves, he advances his core thesis: any asymmetrical frequency curve of a moderately skew character can be resolved into the sum of two separate normal distributions. This is the paper's most significant and audacious mathematical claim. Pearson presents the general equation for this compound curve in its verbal form. The frequency of a given measurement is expressed as a function that is the sum of two terms. The first term is a constant representing the total number of individuals in the first subpopulation, multiplied by an exponential function, whose exponent is the negative of the squared difference between the measurement and the mean of the first subpopulation, all divided by twice the variance of that first subpopulation. The second term is a parallel construction for the second subpopulation, with its own distinct total number, mean, and variance. This formulation is a direct mathematical embodiment of his biological hypothesis. The overall lopsided curve is conceived as the superposition of two symmetrical bell curves of potentially different heights, positions, and weights. The evaluation of this claim is twofold. Mathematically, it is an ingenious piece of analytical reasoning. It provides a flexible 5-parameter model, the 5 parameters being the two means, the two standard deviations, and the ratio of the sizes of the two subpopulations, capable of generating a wide variety of skew shapes. Pearson demonstrates through graphical illustrations how varying these parameters can produce curves that qualitatively resemble those seen in real biological data. The logical coherence of the mathematics is robust. It is a valid and powerful function for modeling asymmetrical data. The deeper evaluation, however, concerns the connection between this mathematical model and the biological reality it purports to describe. Pearson presents the two-component normal mixture as the definitive solution for the kind of skewness he observes. The unstated assumption is that this specific mathematical form is the correct one, because the underlying biological process involves the mixture of two distinct racial types. The model is therefore theory-laden from its inception. While it provides an excellent descriptive tool for fitting a curve to data points, its claim to be a mechanistic explanation of the data's origin relies entirely on the initial, unproven biological premise. The elegance of the mathematical solution risks being mistaken for a proof of the biological hypothesis. Section 3. The method of moments as the analytical engine. A theoretical model, however elegant, remains an abstraction without a practical method for applying it to real-world data. Pearson's third major contribution within the 1894 paper is the invention of precisely such a tool, the method of moments. This is the operational core of his work, the engine that connects the abstract equation of the compound curve to the raw numbers of empirical measurement. His claim is that by calculating a series of statistical moments from the observed data, one can reverse engineer the problem and solve for the 5 unknown parameters of the two underlying normal curves. He defines the moments of the distribution about its mean. The first moment is always 0 by definition. The second moment, designated mu sub 2, is the variance, a measure of the spread of the data. The third moment, mu sub 3, is a measure of the asymmetry or skewness. The fourth moment, mu sub 4, relates to the peakedness or kurtosis of the distribution, and so on. Pearson's procedure requires the calculation of the first 5 moments of the observed frequency distribution. He then derives a series of complex equations that relate these 5 calculated moments to the 5 unknown parameters of his theoretical model: the two means, 2 standard deviations, and the population ratio. The climax of this procedure, and a testament to Pearson's computational fortitude, is the derivation of a nonic equation, a 9th-degree polynomial, whose roots hold the key to unlocking all the parameters. The claim is that by solving this formidable equation, a task of immense labour in a pre-computational age, an investigator can uniquely determine the characteristics of the two supposed subpopulations that constitute the observed sample. Evaluating the method of moments reveals it as a work of statistical genius, a fundamental contribution that would become a cornerstone of statistical theory for decades. The logic is internally consistent. It provides a systematic, albeit monstrously complex, procedure for parameter estimation. The practical critique, however, is substantial. The calculation of higher-order moments, particularly the 4th and 5th, is extremely sensitive to sampling fluctuations and outliers in the data. Small variations in the tails of the distribution can lead to large changes in these moments, which could then precipitate wildly different solutions for the final parameters. Pearson addresses this with a degree of academic bravado, suggesting that large sample sizes are the cure, yet the stability and robustness of the solution from the non-like equation remain a point of vulnerability in the practical application of his method. The claim of a unique and accurate decomposition is thus conditional upon having a very large and well-behaved dataset, a condition often unmet in the messy practice of biological collection. The method is a powerful invention, but its precision in practice could be less than its theoretical formulation suggests. Section 4: Empirical validation, through illustrative cases, to substantiate his theoretical framework and demonstrate the power of his new analytical method. Pearson dedicates a significant portion of the paper to a series of practical applications. His primary and most celebrated example is the analysis of frequency distributions of the ratio of forehead to body length in a sample of 1,000 Naples crabs Carcinus minors. He presents the raw data in a frequency table and proceeds to apply his method of moments. He calculates the first 5 moments from the crab measurements, constructs the non-like equation, and solves it to obtain numerical values for the parameters of the 2 posited underlying normal curves. He then plots the resulting theoretical compound curve atop the histogram of the observed data. The visual fit is impressively close. Pearson presents this correspondence as strong evidence for his central claim that the sample of 1,000 crabs is not a homogeneous group but is, in fact, a mixture of 2 distinct crab types, one with a relatively larger forehead ratio than the other. He interprets this result as a snapshot of evolution in action, a population undergoing differentiation. The critique of this specific claim must separate the descriptive success from the causal inference. The method has undeniably produced a mathematical curve that fits the data well. This is a significant achievement in statistical modeling. The claim that this fit confirms the biological hypothesis of a mixed population is a much larger leap. An alternative hypothesis, for example, could be that a single, homogeneous population, subject to certain developmental or environmental pressures, could also produce a skew distribution. The goodness of fit of the 2-component normal model does not logically exclude other potential causal models. Pearson's interpretation is privileged because the model was built on that very assumption. He also applies the method to several other datasets, including the heights of St. Louis schoolgirls, the petal counts of buttercups, and even a distribution of barometric heights. The inclusion of the latter is particularly telling. It is difficult to argue for a biological model of 2 mixed races of atmospheric pressure. This suggests that Pearson saw his compound curve as a more general statistical descriptor of asymmetry, even while his primary interest and rhetorical framing were firmly rooted in evolutionary biology. The evaluation of this section concludes that Pearson successfully demonstrated his method's capacity for creating accurate descriptive models of skew data. His assertion that this descriptive success amounts to a verification of a specific, underlying evolutionary mechanism remains an interpretation, a powerful and influential one, but an interpretation Section 5, the polemic for quantitative evolutionary science. The concluding sections of the 1894 paper function as both a summary of the technical results and a manifesto for a new approach to biological science. Pearson's claims here are broader and more philosophical. He argues that his work provides the necessary tools to place the theory of evolution on a firm quantitative footing. He suggests that by dissecting frequency curves, biologists can move beyond the vague and merely descriptive accounts of species and the variation that had characterized the field. The new mathematics, he asserts, allows one to measure the sources of variation, to quantify the intensity of selection, and to analyze the progress of differentiation within a species over time. He envisions a future where the naturalist's collecting trip is followed by the mathematician's rigorous analysis in the laboratory, a partnership that would elevate biology to the status of a mature physical science. He explicitly claims that this mathematical theory of evolution can provide a quantitative measure of the progress of the race. This is a bold and polemical claim. It positions his biometrical approach as superior to the traditional morphological and anatomical methods of his contemporaries. The evaluation of this claim must acknowledge its immense rhetorical power and its historical significance. Pearson was effectively laying the groundwork for the field of biometry and challenging the established biological community to adopt a new, more mathematical mode of thinking. The internal validity of the claim, however, depends on the strength of the preceding links in his logical chain. If one free accepts that his method accurately dissects populations into their constituent racial parts, then his conclusion that this provides a quantitative handle on evolution follows. But as previously established, the link between the mathematical model and the biological reality is one of plausible interpretation rather than definitive proof. Therefore, his claim to have created a complete quantitative theory of evolutionary progress is an overstatement of his actual achievement. What he had created was a revolutionary, powerful, and general suite of statistical tools for describing variation. The direct translation of these statistical descriptions into evolutionary mechanisms was a program for future research, presented here with a confidence that outstripped the available evidence. His work was a brilliant prologue to a quantitative theory of evolution, a necessary and foundational first step, but presented with the finality of a completed journey. Conclusion: the architecture of a new science. Karl Pearson's 894 contributions to the mathematical theory of evolution is a work of profound intellectual architecture. Its claims, evaluated internally, reveal a masterfully constructed argument that proceeds from a biological problem to a mathematical formulation to a practical computational method, and finally to a grand vision for the future of a scientific discipline. The evaluation identifies its central claims that asymmetry in biological data signals evolutionary action on heterogeneous populations, that this asymmetry can be mathematically modeled as a mixture of two normal distributions, that the method of moments provides a practical engine for fitting this model, and that this entire apparatus constitutes a quantitative measure of evolution itself. The analysis reveals the immense strength of the paper in establishing a new paradigm for statistical description. The system of frequency curves and the method of moments are lasting contributions of the first order. The paper's claims are strongest in the domain of statistical methodology and weakest in the certainty of its biological inferences. The superb fit of his curves to data, particularly in the Nable's crab example, is a powerful piece of descriptive modelling. The assertion that this fit is a definitive proof of the underlying two-population model is an inferential leap, one that mistakes correlation and model fitting for direct causal evidence. The enduring significance of the 1894 paper, therefore, is its successful establishment of a new research program. It provided the essential mathematical language and analytical tools that made the statistical study of variation a viable and rigorous enterprise, while its specific biological model of skewness was eventually subsumed by a broader family of Pearson curves and alternative explanations. The fundamental claim that mathematics could and should be the grammar of evolution was powerfully and irrevocably made. The work's genius lies in its construction of a complete, self-contained system of thought, one that equips future generations of scientists with the means to quantify the very fabric of life, even if the ultimate interpretation of that quantification remained a subject for a century of subsequent debate.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.